if we have a y equals ab to the x plus c model, this is an exponential with a growth factor b, and turns out asymptote c. Now, c is the asymptote because if b is bigger than 0, then a large negative value of x is going to make this term very small. Raise a number greater than 1 to a negative power, and it's going to get smaller. And a large negative power will make this thing vanish so that y approaches the value c. If b is smaller than 1, then larger positive powers will make it increasingly smaller, and it will approach 0 for positive x, and again we'll have an asymptote c, but this time as x goes through positive numbers. So the asymptote, if we know the asymptote of a data set, if we've got data and in some way we know or think we know what the asymptote is, and the asymptote is, let's say, y equals yf, then this value yf for the asymptote is what goes in for c, and when we take our data points and substitute them into the form y equals ab to the x plus c, that's what's going to substitute for c. Of course, x1 and x2 will solve what will substitute for x and y here, and x1 and y1 here, and x2 and y2 will substitute here. Yf will substitute for c in both cases. Then we solve these equations to get a and b. And we do that by means that we'll see later when we look at solving equations. Then we'll have a model, a y equals ab to the x plus c model, where the asymptote is y, which we called yf over here. Remember, yf, we saw it here, was the value of the asymptote, and that's c. In the case of this curve, a is positive and b is negative, because a negative b, remember, makes this term vanish as x increases. A is greater than 0, so that when x is 0, we have a plus c. If a is positive, then that means we're going to be above y equals c. If a is negative, that means when y is 0, we're below y equals c. And if b is still less than 1, we still have an asymptote here as we go into positive values, but we're going to come up from below. And for example, a temperature function can do either of these, can follow either of these behaviors. And this process also works if we use a y equals a e to the kx plus c. We simply have to substitute the yf, the asymptote value for c, and then x1 for x and y1 for y, and get one equation. X2 and y2 gives us another. Looking now at the transformation process, and going through this relatively quickly, we have x equals y, we have y equals af of x versus x. If we know what function is acting here, we can use its inverse function to transform y. So we have we have f inverse of y versus x, and this should linearize the data if we do use the inverse function. And assuming that it does, then we're going to end up with a graph that looks something like this, of f inverse of y versus x. And when we do our y equals mx plus b, well, y is the f inverse of y, so it's f inverse of y equals mx plus b. And then we solve the f inverse of y equals mx plus b equation for y by applying the function f, which is inverse to the function that we use to do the transformation, to both sides of the equation. When we do that, we get a y value, which we then bring back over here and plug the x's into the y function and compare with what we actually got. Examples of inverses: if our f of x function was x squared, then f inverse would be the square root of x. If f of x was the square root of x, f inverse would be x squared. If f of x is 10 to the x, then we're going to use log x. If f of x is a b to the x, we're going to still use log x. And if we use log x, we could also, of course, use natural log of x.